Okay, well, we're in Chapter 4, and we're going to be talking about operational amplifiers. Now, an operational amplifier will have some voltage in. The voltage in can be on the positive side or the negative side, and some voltage out. It has voltages supplied to it, a plus voltage and a minus voltage. Now, if you remember your proto board, you have the same thing. You have a place for a plus voltage and a minus voltage on that proto board. And your power supplies are that way too. So all your power supplies are dual power supplies, so you could have plus and minus voltages if you cared to use them, which until now you wouldn't have cared, but now you might care. Okay, now what happens is that the operational amplifier is going to have an infinite impedance on the input. So an ideal guy, infinite impedance, I'm not going to use any signal that I'm getting. I'm not going to degrade the signal any, I'm going to just use it. It's going to have an infinite amount of gain for the output, and the output impedance is going to be 0. This is the first active device that you are going to be associated with. So before, your resistor, your capacitor, your inductor, those guys were all passive devices. They did what they did. This guy's an active device. It's going to add things to your circuit, make your circuit work differently. Comes in various shapes and forms. We're going to basically be using one that looks like that, but they can be different than that. Operational amplifiers we've been using for close to 40 years now. They have inside the chip, they have a circuit. Do we care what that circuit looks like? No, probably not, because we can't see it now. Like we see it later. Can't do anything about it. It's there.
Can't fix it.
But there's an amplifier that's a differential amplifier, amplifying the difference between the two inputs, the two voltage ends. There is a gain amplifier in the center section, and then there's a power amplifier giving you power on the output. But all that really doesn't matter. There's nothing really special about what's going on here any, and I don't see anything special about what's going on there. And clearly we have operating curves that do other things. Now, what happens is, let's see if I can, why is it, I wonder, that I don't have a copy and paste guy associated with this thing? View. Screen capture toolbar. There we go. Okay, so I've got the toolbar. Let's see if I can use it. Oh, isn't that nice? Okay, so now we've dealt in the past with things called grounds, have we not?
Yes.
So we've had a ground, and we've had a digital ground, right? So today we're going to have a virtual ground. Now, a virtual ground is going to be a ground to voltage, but no current can flow through it. Okay, so it's a voltage ground, but no current is flowing. Now, how is that possible anyway? This guy up here, he must be doing something. He must be smoking something weird. How can you ground something out, have the voltage go away, but have no current flowing in it? the only way you can do that is blow a fuse, right? So you could blow the fuse, and then there'd be no voltage, and there'd be no current, right? All right, well, on an operational amplifier, I'm amplifying the difference between the plus and minus guy, and I'm amplifying it by lots and lots. Okay, so what is the difference? What is the difference between the plus voltage and the minus voltage? What is that difference going to be? Well, it's going to be 0. So now we do a virtual ground by doing a dotted line. So so now at this point, I'm grounded. Okay, but an operational amplifier has infinite impedance. So the impedance N is infinite. So that means no current can flow that way. No current. And therefore, now I'm at 0. Whatever the voltage was here, I'm at 0 there, but no current's going this way. Where the heck is the current going? Well, it's going to have to go that way, right? So now the current's going that way and is going out, and I have some voltage out associated with it. Okay, so we have a virtual ground, a ground to voltage, but no current can flow through it. Okay, now I'm going to send a signal in, so I got some voltage going into my operational amplifier, but my power supply is plus and minus 14 volts. Can I get anything out of this higher than plus or minus 14 volts? No. In fact, I can't get anything higher out of this than plus and minus 13.3 volts, because there's going to be a 0.7 drop across the diode inside the operational amplifier. So if I put plus or minus 14 volts on the operational amplifier to power it, my maximum output voltage is going to be plus or minus 13.3. All right, well, and when we're not doing something cool, like following the waveform, we're going to be in saturation. I can add a DC offset to the signal, and so I have the capability of throwing in some DC and raising the signal or lowering the signal some. I could go, if I put a resistor on the plus side here, I'm basically saying my ground is no longer 0, so I put a DC offset. That's what that guy's going to be doing for me. I can also go and put a DC offset by going through 2 of the pins of the guy. So I'm doing a null adjust of the operational amplifier. I'm adjusting where 0 is. If I put a variable resistor in the feedback path, then I can have variable feedback as well, variable gain. So I can change the gain, I can change the null. Want me to wave my hands more? Now, this is a non-inverting operational amplifier. If we go back to this guy, my input comes in, and I do something like that, my output goes out, and it inverts. I'm coming in the negative terminal, so when I'm positive on the half wave on the input, I'm going to be negative on the output. When I'm negative on the output, I'm going to be positive on the input. So this is a inverting amplifier. This is a non-inverting amplifier. I'm coming in the positive side. And very good. So we're gonna go. RI for the input, RF for the feedback, and VN. And I have a virtual ground. Maybe I have a virtual ground. I have a virtual ground sitting right there. So what is the current going through the input resistor? Let's see, V is equal to IR, so current has to be voltage in divided by resistance in. Okay, so that's the current flowing through that resistor. What is, and this is right here, I'm at 0 volts. What is the voltage drop across the feedback resistor? Voltage across the feedback resistor has to be the current Vn divided by Vi times Rf. What is the voltage out? If I were at 0 here and I had some voltage across the feedback resistor, then my voltage out must be whatever that voltage feedback is, which is Vn divided by Vi Rf, and it's going to be a minus voltage because I dropped. I went from 0 and I went down when I went past that guy. Okay, so now I can rewrite that and say V out divided by Vi is equal to minus Rf over Ri. What's V out over Vn? That's my voltage gain. So my voltage gain is V out over Vn, and it's going to be minus Rf over Ri. So the voltage gain of the inverting amplifier is going to be minus Rf over Rn. Now does that mean the gain is negative? No, it doesn't mean the gain is negative. It means the sign is inverted. So the signal is inverted. The gain is always going to be VRTED is inverted. That's what that negative sign means. It doesn't mean I have negative gain and I lost signal. It means my signal was inverted because it's a negative, because it's a inverting amplifier. So I've got some Vn. I know the voltage there has to be 0, so that means my current through that resistor has to be Vn over Vi. That current has to flow through the feedback resistor. The voltage across the feedback resistor has to be Vn divided by Vri times resistor feedback. That voltage has to be minus whatever the output is, because I went down. So the output voltage divided by the input voltage minus Rf divided by Rn. Now, we do that, but what do we remember? Well, in the case of most of you, not very much, but if you're going to remember anything, it's going to be the voltage gain. The voltage gain of an inverting amplifier is minus Rf over Ri. Okay, now we got to do it again. So now we got this guy here, and the difference between the plus and minus terminal is not very much. It's absolutely nothing, because if it was anything at all, it'd be multiplied by infinity, and I'd be in saturation, right? So that means that I have to have Vn sitting there as a voltage as well. I have 0 sitting down there, so what's my current through this guy, my current's going to be going that way, right? Because this is at a higher voltage than ground is, and my current's going to be Vn divided by Ri. Okay, well that same current had to go that way, so my voltage across the feedback resistor has to be Rf over Rf times Vn divided by Ri. So what is V out? Yeah, so that's that. And at that point, I get the wrong answer. So whatever I'm doing is wrong. So the right answer is the voltage gain of a non-inverting amplifier is going to be 1 plus Rf over Ri. And I don't see how what I'm doing wrong that won't allow me to get that today. But when we get back to the devices class, I'm sure I'll get it right by then. So for the voltage gain non-inverting amplifier, 1 plus Rf over Ri. Okay, back to our PowerPoint. Maybe, yeah, that?
Yep.
All right. All right, so now we have a thing called a voltage follower. I come in some voltage on the plus guy. I have no voltage difference between those two, so that means whatever my voltage in is, my voltage out has to be the same, and now I'm getting the same voltage in as I'm getting out. Now, why would we bother with such a stupid thing anyway? I mean, I have 5 volts, and I'm going to put this thing, voltage follow, in there, and I'm going to get 5 volts out. What good did that do me? Did that do me any good at all? I had 5 volts, I got 5 volts. I've got an AC signal that's going plus or minus 10 millivolts. I got something over here going plus or minus 10 millivolts. Why bother? Huh? Uh-huh. Oh, yeah, you want the nuclear weapon to blow up. Yeah. Let's say I've got a very delicate signal over here. So I've got some antenna thing, and I've got some itty-bitty current coming off that antenna giving me the voltage difference. I go through a voltage follower, I add power. This thing can now, the voltage out can now have watts of power associated with it. Whereas the input signal may not have had any power associated with it at all. It may have been some communication thing that is very fleeting in nature. So I can have a voltage follower. All right. I can have a summing amplifier. Now, how can this guy sum anyway? Let's see. So this is saying if I've got 2 of these guys, R1, R2, and I'm going into the negative guy, and I got some feedback resistor, and I'm grounded on the positive side, so I got something that looks like that, and let's say I got 1 volt here, and I got 2 volts there. And then let's say this is a 1K, and this is 1K, and this is 1K. I still have a virtual ground sitting right there. So my current through R1 is going to be 1 milliamp, going that way. my current through R2 is going to be 2 milliamps, 2 volts divided by 1K. My current going that way has to be the sum of them, 3 milliamps. 3 milliamps going through 1K resistor gives me 3 volts. It is going to be minus 3 volts because I am an inverting amplifier. But I just added 1 and 2 and got 3. Okay, so before the advent of the digital computer, we had analog computers. So coming out of the World War II into the Korean War, into the Vietnam War, we were using analog computers. So we'd use a summing amplifier to sum something. Okay, and that's what we were doing. We could change the resistors on these guys, and we could even get more complicated. So let's say we had this guy be 1K, and that guy be 2K, and this guy be 4K, and this guy be 8K. And we're going to go into a summing amplifier. RF. Well, now what we're doing is we can take a digital signal, 1, 0, 1, 0, and this is my most significant bit, and this is my least significant bit, and I can change it into an analog signal in my summing amplifier. So now I could do digital to analog conversions in a summing amplifier by just changing the value of the resistor. The more resistance, the less current. So my least significant bit gets less current. My most significant bit gets 8 times as much. Okay, so I could do that if I wanted to. Summing amplifiers. Now I'm taking the summing amplifier and I'm deciding that, you know, I really don't want to sum it to get the negative answer of what I'm getting. So I'll just throw in another amplifier, and now I'm going to sum these guys. That's fine. But when my voltage out is gonna be, what happened? My voltage out. Thank you very much. How far do I have to go back? There we go. So now I'm summing them. I'm getting a negative answer there. I'm taking that negative answer and I'm making it a positive answer on my V out. So now I don't have to deal with 1 plus 1 is minus 3 anymore. I can have 1 plus 1 being 3. Much better, right? I think so too. I can add this is a differential amplifier. All I'm doing is I'm just trying to figure out what the difference is between the 1 and 2 guy. So I'm not, this would be a compare amplifier. So I'm comparing signal 1 and signal 2. If I'm positive, then signal 2 won. If I'm negative, then signal 1 wins. And I'm going to go there, and I'm going to be saturated pretty quick when I'm doing that. This is a voltage to current converter. So I'm going to have whatever voltage I have coming in, that's going to give me a current coming out, and it's going to be independent of the load. So the load could be 1K or 2K or 10K. It doesn't matter. This guy is going to give me the same current. So back in your circuit analysis class, we had voltage devices, right? Batteries, and then we had DC current things. And well, how the heck, how can you have a DC current thing that's going to put out 10 amps all the time? You know, that seems dumb, right? Well, now we have one. I can now have a current, a constant current device. I can also go current to voltage converter. So whatever my current in is, my voltage out is I'm gonna get voltage instead of getting current going to the load. clearly I'm going to have both. I can have an operational amplifier that integrates. So I've got a voltage in as a square wave, and I'm getting a waveform out, which is the negative because I'm an inverting amplifier, but I'm getting the area underneath this curve sitting right there is the area of the square wave. So now I can integrate using an operational amplifier. Now I can go, and this is back in 1968 or so, we're doing missiles testing, and AT&T was trying to shoot down missiles over Hawaii for the heck of it. And you know, for your entire adult life, you've heard of our missile defense system, right? And we're going to do it. We're going to do it. We're going to do it. Well, in 1968, we're doing it already. The AT&T guys were knocking out warheads out of the sky using analog systems like this to calculate what course I want to get down to intercept it. And the Air Force said, "Quit doing it. You're ruining our test drones." So they had to make it so it missed, so that it wouldn't hurt it. Anyway, and so now Israel's got an Iron Dome thing, and we have Patriot missiles and other things. If we really wanted to do it, you know, we'd do it. We'd rather just bomb them first, but you know, that's a different issue. So, but all I do is I put a capacitor in the feedback loop, and now I've got a integrator, and now as my voltage input goes as a square wave, I end up adding the area of the square wave, giving me a triangular wave. Triangle. Yeah. And we go further on that, but I'm not using English words anymore. So if I put the capacitor on the input of the operational amplifier, then I have a differentiator. So I can do differentiation, I can do integration, I can add, I can subtract, because if I have a negative number, I can subtract it, right? Can I multiply? Yeah, if I have a gain that's multiplication. Can I divide? Yeah, I could have a gain that was less than 1, and that'd be a divide. So now, with operational amplifiers, I can add, subtract, multiply, divide, integrate, and differentiate. Can I take a square root? Not easily. But now I can do pretty complicated things. So now I'm taking the differential. If I'm taking the derivative of this function, the derivative of a straight line is going to be 0. The derivative of something that's straight line vertical is going to be infinite. So I'm seeing a peak. I'm seeing that being something that's peaking out. And on my oscilloscope, it's really going up very high. It's just that my oscilloscope's not going to see it because it's going to get down before the light turns on. So now my differentiator is telling me, am I going positive, am I going negative on my waveform? And when if I have a waveform that looks like that and I want to differentiate it, the slope of that line is some constant number. The slope of this line is some constant number, and the reason the positive slope is negative and the negative slope is positive is why? Because it's an inverting amplifier. Right, exactly. Steve got it already. All right. But that's what I'm going to do. So if I send a triangular wave in to a differentiator, I get a square wave out. If I send a square wave into a differentiator, I get peaks out. And at that point, if you're doing it in a lab with real equipment, you're probably turning off the lights in the lab because it's going to be very faint on your oscilloscope. It's going to happen very quickly. Now we've got a compare circuit. So I've got some reference that I'm comparing to, some voltage in, and as I go above the reference point, I go saturation high. When I go below the point, I go saturation low. So I'm comparing it. I want 25 cents to give you a Coke. Until I get 25 cents, I don't turn on. As soon as I get above 25 cents, boom, I'm on. I can go in and change my reference point a little bit. I've now put the reference on the positive side, the in on the opposite side. Now I have a little bit different waveform, but I'm doing the same thing. Okay, now I'm changing my reference point. So I got a variable guy. Now I can set my reference point. So I want to count 13 bottles of beer, or do I want to count 10? High-speed dual comparator. So yes, I can buy one, or buy a data sheet. All right, now we have filters that we deal with next, and so if I have something that looks like that, and I got some V in and some V out, when frequency is low, this becomes an open and my voltage out stays high. When frequency is high, this becomes a short and my voltage out goes down. So if I look at the curve, it looks something like that. And we would call that a low pass filter. And if we had 10 volts on the input, how many volts would we expect on the output? Some number less than 10, because I have a resistor in the way, right? So my voltage out is always going to be less than my voltage in on a low pass filter. Alright, so now I go and I put a low pass filter on the positive side of a voltage follower. What's going to happen? Yeah, so now I'm gonna get the same thing, except now I'm gonna because it's a voltage follower, but this is the same thing. It's gonna be a low pass filter. So when at low voltages I have something going to the plus guy, at high voltages I don't. Okay, I've got some voltage out. I have some voltage cutoff point. I got some roll off. I've got some half power point, which is 3 dB down on my power curve. 6 dB down if I'm doing voltages. Now I can daisy chain these guys together, and now I have a fourth order active low pass filter. So in a regular low pass filter, I've got 20 dBs per decade, and my slope going down. Now I've got 20, 40, 60, 80 dBs per decade because I have 4 of these guys put together. So this is a first order filter, but it's 4 of them. 4 first order filters, boom, 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 daisy chained together. Then I can do a second order low pass filter. Now the word order is something we don't use very often, right? So in our math classes we use degree, and degree means x to the 4th, so that'd be a 4th degree guy. When we use order, we're talking about a differential equation, so a second order differential equation, a 4th order differential equation. And that's the same thing that we're talking about here when we're talking about a second order active low pass filter. We're taking that differential equation talk from our math classes and throwing it into the electronics world, where it doesn't make any sense at all, but we're going to accept it anyway. Okay, so basically I've got two low-pass filters going on. And I see this guy's going to have 40 dBs per decade. A decade means a power of 10. So if I go from 100 hertz to 1,000 hertz, that'd be a decade. If I went from 100,000 hertz to 1 megahertz, that'd be a decade. But this is going to turn off what's going to be passed very quickly, 20 dBs per decade. Here I've got a unity gain, second order, active low-pass filter. So whatever my voltage in is, that's what my voltage out is going to be. Depending on what frequency I have coming in will decide how much of it actually gets out. Now I have a high-pass filter. So if I go and I put my capacitor there and my resistor here and call this V out and call this V in, when frequency is low, this becomes an open, and when frequency is high, that becomes a short, and I have something that looks like that. It's my transfer curve, and that becomes a high pass filter. And now I can take my high pass filter and I can stick it on an operational amplifier, and now I'm not degrading the input signal any, and I'm giving it some power on that voltage out. And here's our voltage transfer curve. As I have more hertz, I have more of my signal being sent out. Anybody remember what the cutoff frequency is? Is it 1 over LC? 1 over RC? 1 over 2 pi RC? Something like that. Well, when we get to the devices class and we care, then we'll remember.
1 over 2 pi RC?
1 over 2 pi RC.
C1.
Yeah. So second order high pass filter. Wherever the low pass filters capacitors were, now that's where the resistors are. Wherever the resistors used to be, that's where the capacitors are. So that in our other application, we had a resistor there, capacitor there, capacitor there. Now we've changed the positions of the capacitors and the resistors, and we have a high-pass filter. High-pass filter is going to have a 20 dB per decade cutoff, roll-off, unless it is second order, then it's going to be 40, or third order, or fifth order. So here we have, now we have a bandpass filter. So I've got a high pass filter and a low pass filter together. So if I look at that, I say, well, I got this low pass filter doing that, and I got this high pass filter doing this. What am I going to see? I'm going to see the middle part. So I'm going to see this part here. Okay, so that's a bandpass filter. I'm passing the guy in the middle. And that's the way we tune our AM and FM radios. We change the capacitance by turning a knob, and that change in capacitance changes where the bandpass is of the filter network, and that's how we get 1290 kcar instead of getting 1110. And here we are, we see two of them, we see some cutoff points, we see some bandwidth between the cutoff points. And we're calling this a Bode plot. In multisim there is a Bode plotter, and when it comes time in your lab work to get to that point, you'll figure out where the Bode plotter is and use it. Well, what's happening here? This looks like an instrumentation amplifier, maybe. No, it's a band elimination filter. So it's got a high pass filter and a low pass filter, and it's eliminating them. It's eliminating the guy in the middle. So instead of doing that, it's got something that looks like this and something that looks like that, and it's passing both of them. But whoever's in the middle, we're rejecting it. So someone's out there trying to jam my radio. One of the second-year students who built the AM transmitter is out there trying to jam 1290 KCAR, and I can't get it. And along with a lot of other things, because it's jamming a lot of stuff. And so I make a band reject filter to get rid of the jamming going on. You don't want your daughter using her cell phone in her bedroom, so you sneak in there with a band reject thing. Well, anyway, maybe you do that. There are certain dads that might do something like that. Okay, now we're going into the instrumentation operational amplifiers. Now, most of these guys are just encapsulated inside of a chip. It's not like we're building components to make these things. We're buying chips that already have them in. So now I've got a voltage in, a voltage out. I got a variable gain that I can tweak on, and I can either be a dual power supply or a single power supply. This is a normal instrumentation amplifier in all of our hospital applications. So if I want my blood dropping whatever it is gizmo thing to drop a blood every half second into me, then this is the type of thing I'm going to be using for my instrumentation. It's a very stable thing. It's very well known. Again, I'm not going to build it from scratch. I'm just going to use what's there. We have a lot of them, and that is just so wonderful. If we could see the gains, which I don't know if you can, but it's saying the gains are between 5 and 10,000, 5 and 100,000. So I have plenty of gain to go around. I mean, that's not the issue. All right. So now I've got a CDA. Anybody got their book open to know what a CDA is? Huh? What?
Current difference amplifier.
Oh, a current differential amplifier.
Current difference.
Current difference. Okay, so again, I bought this special. It's gonna amplify the current difference, not the voltage difference. I don't recall ever seeing this in any application anywhere, so that's why it's in the book, naturally. So that's a simplified view of what's inside the amplifier. I'm sure I won't have that on any test either. It can be biased, so that I can go up and down in current. It can be okay, so this would be the inverting one. I guess the other one was not inverting, and I didn't look at it. Now, the capacitor sitting here on VN is not there for filtering. It's there to block the DC from getting to it. So we normally put capacitors that are DC blocking capacitors in operational amplifiers and transistors both, to maintain the biasing of the transistor and only allow the AC signal to get to the base. So this guy's only going to let the AC signal get by him. The DC component is going to get filtered out. And wow, look at that. I got a sine wave going in, I got a sine wave going out. That's just so special. And there we go again, another sine wave going in, sine wave going out. A data sheet. Oh, this is the what problem? Does anybody know what problems I'm supposed to work? I didn't bring my book with me, so. Why don't we go back to, does anybody have a syllabus? No. I mean, I could get one here if I really worked at it, like 30 seconds. We'll race. Well, the issue is how far through chapter 4? Am I supposed to finish chapter 4 today? Or I was supposed to finish it last week?
Yeah,
obviously you're
Monday of last week.
obviously you're reading the syllabus
Today
wrong.
was supposed to be 5-1 through 5-9.
This is the lab syllabus, so it doesn't do any good.
Give them our tech math syllabus.
1, 4, 5, and 6.
Well, it looks like we're a week behind already. All right, so if we just go 1, 5, and 6 today, and then follow 1, 2, and 18 in chapter 5, next period, we will have caught up. That's 1, 4, 5, and 6. I got it. Except I don't have a book. That's all right. I'll borrow Steve's. Oh, Steve doesn't have a book either.
Chris,
I just follow the
I don't use it.
All right, so I'll borrow Chris's book. And, this thing's so heavy. I don't believe you got it heavy. 1, 4, 5.
The syllabus. Why you bring your sheet?
So now the issue is, how did we get so far behind? Yeah, it doesn't matter.
Snow day.
Oh, it was a snow day?
And close today and.
It closed today. Yeah, that's probably what happened. All right, I'm almost there.
1, 4, 5, 6.
Right, I got it. I don't know. 213 in this book. I don't know what it is in a real book, though. Number 2. Using the gain in problem 1. I don't know the gain in problem 1. What is the maximum input voltage swing needed to avoid clipping the output? Okay, now, so now that means I got to go back to number 1.
You're supposed to do 1, 4, 5, and 6.
Oh, I'm supposed to do 1. Now you tell me. Calculate the closed loop gain and output voltage of the amplifier below. All right, so this is a this is an inverting amplifier. So the voltage gain of a inverting amplifier is minus RF over RI.
And that's what claim that is beautiful.
What? Are you complaining about something?
All of it.
All right, so 590, 510 ohms divided by 10 ohms, 10K. So my gain is going to be 51. All right. Calculate the gain. And what's going to be the output? Okay, so my output voltage, V out, can be plus or minus 11.3 volts. Because there's a diode in the circuit that's going to do that. All right, well, so much for number 1. Oh, have to do something about it, move it up.
Yeah, thank you.
So that's my gain.
Plus or minus.
And my voltage out could be plus, anywhere between plus or minus 11.3. 1-4. Calculate the closed loop guy in 6. Okay, so 4. Calculate the closed loop gain and the output voltage in 6. Okay, so my gain, my voltage gain of an inverting amplifier is minus RF over RI, 330K divided by 50K, also known as 66. Gain is always dimensionless. There's no dimensions associated with the gain. I have an input signal, so my VN is 500 millivolts. So my V out is going to be 66 times 500 millivolts. What's half of 66? 33 volts. Now, it doesn't tell me what my power supply is supplying, right? So I don't know that I'm limited to plus or minus 12 or plus or minus 30. So I could just assume that I'm limited to plus or minus 50 volts and I can get to 33. Stupid thing. He should have told us. And so that's number 4.
You read that up.
Oh. Why? That better? These people that sit in the back row gotta have it all in one row. Now I broke it.
Have Sealand stand there and hold it.
Don't wait for me.
Well, Steve can sit there and hold it?
I didn't say Steve Sealand.
Oh. Zealand can hold it. Oh, here. Is that better? Sometimes. All right. Well, I hope the next two are just as easy.
Which one's next?
I mean, I had to multiply. I had to divide once and multiply once. Wow. I don't know if I can handle that. Number 5. Calculate the output voltage of the summing amplifier in 47, given that I have those voltages. Okay. So this is going to take more than the normal clarity of picture. Why don't I just do it in multisim? 10K, 20K, 10K, now that was professional, if I ever saw something professional there. That's better. 4K, which we're going to disregard totally, and because it's just put in there just to hose us over, making us think we have to use it. 22K, V out. Alright, so I got the right picture, and I got minus 1.2 volts. I got 1/2 volt, and I got minus 2.8 volts. Okay, so that I get a 4/0 on drawing the picture. Okay, now it's probably time to take out our calculator. We have a virtual ground sitting there, which means I have 0 volts sitting there. I have 1.2 volts and I have 10K, giving me 120 microamps, and it's going to be negative because it's going to be flowing that way. So my current flowing this way is a negative 120 microamps. I got a 1/2 volt and 20K. Okay, so I got a calculator that won't work because I don't have enough light up here. Okay, so So I got 0.5 divided by 20K. And now I got my mode set so I can't see it. Oh, you got the answer already?
No, I'm giving you light.
Oh, you're giving me light? Yeah, that's a good idea. Give me light. Okay, so where was I? I was a half volt divided by 20K. I think I just should have done it in my head. 25 microamps flowing that way. And then I got 0.85 divided by 10, 0.28 divided by 10. So I got 280 microamps flowing that way to be negative. Okay, so I'm minus 120 minus 280 plus 25. Okay, so maybe I can do that. 120 plus 280 minus 25. So I got minus 375 microamps. I'm going to multiply that through 22K, and then I'm going to put that answer right here for my V out. Okay, so I got 375 double E minus 6 times 22 double E 3. Boom. 8.25 volts. And I'm going to, because I'm negative here and I have negative current flowing, I'm going to be positive on this side, and this is a non-inverting amplifier. I'd expect that I have negative going in, I'm going to have positive going out. Okay? Move it up, move it down. Do something with it. Okay, so my virtual ground is sitting here. Okay, so that means that my current's going that way, my current's coming this way, my current's going that way, and we should probably have that current going that way just for that to be consistent with my picture. And that, so that means that I add them up, I have minus 375 microamps going that way, going this way, 375 microamps. So this has to be the plus side, that has to be the minus side, this has to be plus 8.25. That answer enough questions or confuse the issue more? But I'm sending in negative voltage on the negative side of my amplifier. Negative and negative is going to make it positive. Alright. I hope number 6 takes at least that amount of time. Refer to problem 5. If V1 and V2 remain the same, what is the value of V2 to have an output of 1.5 volts? Okay, well, this might be interesting. I doubt it, but it might be. Okay, so I've got 10K, 20K, 10K, and V1 and V3 stay the same. So I got minus 1.2 volts, minus 2.8 volts, and V2. Negative, positive, and I got, what I got there? 22K. And I know my V out is 1.5. So now we want to know what is V2. Okay, so I do the same thing. I say, well, I've got a virtual ground sitting there. I have 1.5 volts sitting here. So 1.5 divided by 22K. 1.5 volts divided by 22K gives me 68.2 microamps flowing that way. Alright, now from the previous problem, we remember maybe, if we're lucky, that we have 120 microamps flowing that way, and we have 280 microamps flowing this way. So in order to do that, how many amps do we need coming to this guy in order to make that amp up? Okay, so the summation of currents going into a node has to be 0. That being the case, the current through R2 plus 68.2 minus 120 minus 280 microamps has to be 0. So the current going through R2 has to be 120 plus 280 minus 68.2 microamps. Right? 120 plus 280 minus 68.2. The current through R2 has to be 331.8 microamps. Okay, so the voltage 2 has to be 22K. V is equal to IR times the current. Okay, so 22 double E3 times 331.8 double E minus 6, 7.3 volts. Is what I'm going to have at V2 in order to have 1.5 volts coming out of this operational amplifier. Okay, questions about that?
Can you bring the slide on?
Bring the slide down.
Oh, yeah, there you go.
Okay. Bring the slide down, bring the slide up. Like I say, in order to fully appreciate operational amplifiers, it will only take us a mere month in the devices class. But in the industrial class, we're just going to use them, so we don't have to fully appreciate them. What do we use them for? Well, if I had a 5-volt signal and I had 500 feet of wire, we've already talked about I can't get the signal down the dumb wire. So I throw in an operational amplifier, and we call it a current loop, that adds current to that 5 volts of signal so that it goes down the wire further. Yeah, so that's what we use it for, among lots of 10,000 million other things.